So this is kind of your main hub. Oftentimes I will send out email through this if I need to communicate with the entire class. Where's the thingy thing? Okay, so like I said, the main things here are my contact information and my office hours. The office hours are there for you as a student if you have homework questions, if you don't understand a concept, that kind of stuff. It's not time for us to work on things as an instructor. It's for all students. So if you can make it to any of those times, just stop in. You don't have to email me or anything like that. I'm also in the Math Center on Tuesdays from 3:30 to 4:30. And the Math Center is actually in the library. If you haven't been, it's a great resource for doing your homework and getting help with that kind of stuff. So I'll be in there Tuesdays only from 3:30 to 4:30. The office hours are more like one-on-one. The Math Center is sort of a free-for-all sometimes. So if you do come to visit me in the Math Center, you might not expect like one-on-one attention because there might be other students from other classes in there. So, and I'll submit a ticket. The board looks really fuzzy and not great. So the amount of time is recommended outside of class is 8 to 15 hours. Probably a little bit more than other math classes that you've had up to this point, but it's essentially the same. We have class lectures, then you go home and work on stuff, figure out like where you need help, and so generally 8 to 15, might be more, might be less, depending on the student, but decent amount of time per week outside of class for sure. We're using Early Transcendentals, the 3rd edition, by Briggs, Cochran, I think Gillett and Schultz, the other 2 authors. So you want to make sure that you have access to that textbook, either the physical copy or the electronic copy. So you don't actually need the physical textbook. The bookstore people gave me a price of $280, but I have to call them today and ask. I don't think that's right because last semester was like $414. And I would be shocked if they actually reduced textbook prices. So I'll have to check on that. But if you buy this textbook and or the access code, it will be good for Calc 1, 2, and 3. Because the code follows the textbook, not the course. So $280 maybe for the actual physical book and the access code. The access code in the bookstore is $140, and the access code bought online is about $120. So that's definitely your cheapest option, is to buy it directly through our D2L My Math Lab link, which is here on our main page. This is how you access that. So if you're accessing it for the first time, it's going to prompt you, do you want to access this temporarily or do you want to pay now? And paying now is where you would spend the $120. If you buy the actual access code in the bookstore, it's like $140. So those definitely are much cheaper than the physical textbook. It's totally up to you, but what you have access to online is a full color version of the textbook, and I think it's even better because the textbook access you have online is also interactive. So a lot of graphs and stuff you see aren't just like static images. They're things that you can actually like move around and manipulate to see how it works. So depending on your style, for whatever that's worth. See if that's a word. Calculators. You can use whatever calculator you want for work. I would recommend using a non-graphing calculator for your homework and your quizzes because you can't use a graphing calculator on the exams. So whatever calculator you're going to use, just stick with it. Some calculators vary, like the syntax and how you enter stuff in. So I would just recommend whatever calculator you're going to use, just stick with that so you're totally familiar with it. I know a good cheap one is the TI 36X Pro. So So it'll do a lot of calculus stuff, but on exams you do need to show your work. It's a good cheap calculator to check, like, hey, did I do this derivative right? Did I take this integral correctly? You can check your work with it, but as far as exams go, you should be able to show your work as well. But that's a really good calculator. So no graphing calculators rather on the exams, and no phones, of course, for obvious reasons. I think this calculator is like $20, $18, something like that. So you need internet access because our course components, our assignments and our quizzes, they're all done online. And that access code is the same access code we mentioned that gives you access to the textbook and all of that stuff. So you definitely need the access code. Even if you're not going to utilize the textbook at all, you need to have that access code purchased. If you're still waiting on financial aid, there is a temporary access option that's good for 14 days. So you should be able to, right out the gate, to just get in, start looking around, doing assignments and stuff like that. Okay, and just be aware that you can't buy it any other way. It's either through the bookstore or through the link in MML. If you get it through Amazon or some other outlet, it's not going to work. It's like very specific to D2L. Okay, do y'all have any questions at this time? Yeah.
When I was in pre-calc with Debbie, she had mentioned that some math lab codes will transfer over to other courses.
Right.
So pre-calc to calculus, that does not transfer over.
Correct.
Okay.
Correct. Yeah, the pre-calc will not transfer to calc. It's only it's by the textbook. So since it's a different textbook,
Okay.
yeah, you're going to need to get a new code. If you took this class last semester or the semester before or the semester before, you should be able to get right in. Yeah.
What would be the difference between buying it like through D2L going online or buying it from the bookstore? Is there any difference?
There is no difference if you buy it through the bookstore or online.
Just cost?
Just the cost, yeah, exactly. It's a little bit cheaper online. Any other questions? Yeah.
As far as the exams go, will we even need a calculator? Or
Yeah.
will we given numbers that?
Yeah, I think for the exam there are some problems where you would need a calculator. Just for like the first exam I'm thinking of, there's a couple of questions that are kind of heavy numeric computations. But yeah, I would definitely have a calculator. Unless you're brave and you just want to see what happens, roll the dice. The math department does have like scientific calculators. I think we have like 20 of them. But don't rely on that. Sometimes other instructors have exams on the same day and they'll just take the whole box. So sometimes there's extra calculators available on exam day if you forget it, but I wouldn't count on it. And inherently with technology there's always issues. This dedicated support line is supposed to be for front range students. So you don't have to go through like Pearson, and wait to be directed to the appropriate place. If you have issues like getting it set up or operating correctly on your computer, I would give this a shot first. If they can't help you, then let me know and I'll forward you on to our administrator. But I don't have any privileges in MML to help with most issues. Depending on what like browser, operating system, what kind of add-ons you have, it's all unique. So give that number a call if you have issues. And we'll go over MML stuff in a moment. But again, that's supposed to be a line for front range students. Homework notebook, I don't take up, I don't grade, but I do recommend that you keep some sort of organized system to your homework since it's all done online. I think what I see anyways, there's a tendency to sort of just like click through the homework or jot down a couple of key steps in that homework problem. But when you take an exam, you need to show your work. So you really want to keep that in mind. When you're doing your homework, you want to write the problem out, and keep it organized as you would on an exam. So there's usually a big sort of discrepancy between, doing assignments digitally and then having to take an exam on paper. So practice when you're doing your homework is, of course, to practice the concepts and stuff like that, but also practice being neat and sort of like I want to see your chain of thought, right? It's some problems are pretty straightforward. Other problems involve a couple of steps. If you go from A to C, you're probably going to lose some points. So when you're doing homework online, just please remember that. I think it will really, really help you out. Let's see. We're going to skip this stuff. So we've got basically 3 things that contribute to your course grade. The online homework, the online quizzes, and the in-class exams. The homework online is 20%, quizzes are 10, and exams are 70. So each exam is counted the same. I know some teachers do like finals 20% more, whatever. The final exam is part cumulative and part new stuff. So it's worth the same, it has the same weight as the other exams. The addition to the final is that the final can replace your lowest exam score. So even if you miss an exam and you make an 80 on the final, that 0 on the missed exam will be replaced by an 80 on the final, from the final, yeah. I'll go into some of the details. There are some differences between the homework and the quizzes and how it's treated. But again, those 2 components, 30% of your grade is done online. We'll have 3 exams, and it says a cumulative final, but it's kind of half and half. Half the first 3 exams and half the new material. So at the end of the semester, I use standard rounding. 89.5 is a 90, it's an A, and 89.4 is a B, because it's an 89. So do keep in mind, we have 3 things that contribute to our grade, and only 3 things. I do see a lot of people take, it's just time consuming, right? To do all of these homework assignments at home when you're not working or whatever, it's very time consuming. But the online components are 30% of your grade. So try not to slack on those. We'll look at a grade calculator in a minute and run through some like grade scenarios. And you'll see that if you can keep your homework and your quiz averages at like 90s or above, you can literally make Ds on all of your exams and still pass with a C. So, those things are super important. I've seen people just take exams and honestly make hundreds on every exam, but they didn't do homework or quiz, and so their grade was a C, even though they made 100 on all of their exams. So please, please, please do those things. As far as cell phones go, just make sure they're not distracting people. They're on silent or vibrate. That's kind of the general ethics policy in this class is, I know some people bring their laptops to class and do homework. That's totally fine. But if it's distracting someone, then I won't allow it. So just make sure you're considerate to those around you. I think it's just pretty standard human etiquette. A couple of sources of help outside of myself and my office hours would be the Math Center. Here are the center's hours. It's in L280. So as you walk into the library, you go all the way to the right. It's that very back room on the far right. Has anyone utilized the Math Center before? A few people. Okay, so the way that works is all of the computers are set up so you can do your homework and quizzes in there if you want. Usually there's 1 or 2 people working at a time, and if you have questions, you just raise this wooden stick and somebody comes over and helps you. So that's a really great resource. Hours are provided there. The ASC is a place to where you can create study groups. You can get you can pay for like a one-on-one tutor if you need that, and that kind of stuff. So if you want to start a study group, you can do that. I think you have to have 2 other people. But you would go through the Academic Success Center and say, hey, I've got 2 other people in class. We want to meet every Monday from 1 to 2 o'clock, and they can reserve a room for you. And that's comes with a facilitator as well, somebody that's versed in calculus. So that's a good option if you have extra time and need sort of extra support with the material. I would highly recommend that. People that have done that in the past have made A's and B's in the class for sure. It's just more exposure, more practice. But you can have a dedicated room at a dedicated time throughout the semester for that. Okay. So you'd contact the Academic Success Center for that. Do y'all have any questions about any of that?
In other math classes I've had, there's been like a student instructor in the course. This one doesn't have it.
No, yeah. So if you've taken like algebra, stats, some other classes here, they do have a supplemental instructor that sits in the class and does study sessions. The upper level math classes don't have that yet. So there isn't an SI for our class. It's just basically us, the Math Center, and if you want to form a study group. Yeah, any other questions?
I'm going to provide a list later. So I know there's different instructions that will go to the Math Center as far as like who can actually help us with calculation.
Right. So there's a schedule for like the whole Math Center, but then next to that schedule should be a list of names and what subject they can tutor in. So yeah, that's a good point. Not all the time that you go into the Math Center would be someone who could help with Calc 1. So if you do, maybe I can get some copies of that particular schedule, because I have students go in there and they're frustrated because it's like, hey, that person couldn't help me, and it is frustrating, but not everyone we have working can do all of the subjects. So I'll try to remember to get one of those schedules out to y'all. Perhaps just post it on D2L. Yeah, that's a good point, thanks. Are there any other questions at this point? Okay, let's see, what else do we want to talk about? That's pretty much it. There's your important dates. Payment deadline is the 25th of February. You don't get dropped for not paying, but they do fine you like $100, I think every day or every week. So you want to make sure you're paying by then. And then our schedule. So this is tentative, it's subject to change. Typically I don't change exam days. If we can't get to material, it's either pushed back to the next exam, and sometimes we just haven't had time to cover a certain section that was just totally omitted. So this is subject to change, but I will keep the exam days where they are for sure. That way if you're working, you have advance notice as to when the exams are, and hopefully your boss can work with you. So yeah, that's. We also have on that far column the homework and quiz due dates. Those will also be present in MyMathLab. So you've got a couple of places to remind you of when assignments are due. And I've typically noticed that especially the first quiz is missed quite a bit. So you do have homework and quiz, one quiz for every single unit. Every time we have a test, you'll have a chunk of homework due and a quiz due. So again, in the main page here, this is our MyMathLab link where we're doing homework, quizzes, accessing the textbook. There's study plan, there's multimedia libraries, there's all kinds of stuff. It's not just a glorified thing to do homework on. There's a lot of good resources here. But assignments are here under assignments. Once you've accessed temporarily or paid for the thing, just be mindful that at the end of the 14 days, if you access it temporarily, you'll have to have a permanent code. Everything will roll over, you won't lose anything. But next to each assignment is the due date and the time it's due. I have all of our assignments due the day of the exam. And I understand that that's not kind of beneficial to some. Some people like to have that discipline to say, oh, this homework is due this week and that homework's due next week, and so on and so forth. That's not how I do it. Some people procrastinate, and so I just leave it open till the very end, so you can sort of accommodate your own style. But if you like to have that discipline to say, well, I would rather that be due the first week, just so I know it's due and I will actually sit down and do it. You're just gonna have to discipline yourself to do that, because everything's due the day of the exam for that particular unit. That being said, I really don't recommend like doing all of the homework the day before the exam. There's options through the gradebook to review the homework. I would seriously recommend like keeping up with material as we finish it. That way you're sort of stacking your learning. You're not just cramming for the very to the very end and having all of this information in your head. If you layer it, I promise you'll understand it and you'll retain it a lot better. If you cram, that's fine. I mean, that's totally how I studied. It's just not good for long-term. It's not good for long-term memory. So I would recommend keeping up with the assignments as we complete them in class. Then for the exam, going back and perhaps reviewing the homework, and I will have an exam review with additional problems that you could also review as well. So some people say, well, I like to use the homework to study for the exam. That's fine, but if you're studying all at once, it's sometimes it leads to pretty poor outcomes. So there's really two main differences between the quizzes here with these orangish squares and the homeworks are these circles. The homework, you have as many attempts as you want to get the thing where you want it to be. So like if you can start wherever you want, but if you get a particular question wrong, it'll ask if you want to try a similar exercise to get those points back. So really you have unlimited attempts until the due date to get that homework score where you want it to be. Okay. In addition, you can save your progress. Like if I'm on question 7 and I have to go to work, I can just save that and come back and pick up where I left off. The quiz, you cannot save progress. The software or the MyMathLab almost treats a quiz like an exam. It's really weird because you're timed, and we'll look at that in a minute. But you save your progress here. This section here, that's question help, you can access your textbook through that link. You can print out either a specific homework question or the entire assignment. Some people do that. They'll print off the section, work at home or at work or whatever, and then just come back when they have time to fill it in. So that's certainly an option as well. The other thing, not all questions will have a video link here, but the video in theory should link you to sort of a lecture kind of based on this current principle that or concept that you're looking at. The help me solve this and view an example are sort of more independent. So like if you click on that question help and help me solve this, it'll sort of prompt you and it'll say, hey, remember that this, to compute a limit, blah, blah, blah. And then you can sort of just click through it, and at some point it's going to prompt you to interact with it. So it sort of scaffolds the question. And if you notice, it's the same question that you're currently working on. So it sort of scaffolds you through the problem. The view an example will give you a similar example to the one you're working on, but it won't prompt you for anything. So you can just click through it and read to see how they're explaining how to do the problem. So usually the homeworks will have that. Not all homework questions do have that. I do recommend using those very lightly as well. I think it's hard at first, especially when you're under a time crunch, to sit down and do homework. And as soon as you read a question, you're like, oh man, I have no idea what to do. Let me just click this to see. And then you sort of get in that habit. And then when you get to the exam, you see that question and you're like, oh, hey, the computer thought through that for me. I don't know how to do this problem, right? So I would use those sparingly. I would recommend, like, if you get stuck, just to look at the notes to see, all right, well, what did he do? What did we do in class? Because you don't obviously have this utility on the exam. It's honestly another detriment that I've seen or have heard students say, well, I do the homework and I can get them all right, but I'm using this, help me solve this, review an example a lot. And so when I take the exam, it's not there for me. And that recall, being able to recall like a specific problem or the steps to solve a problem isn't there because the computer's recalled all of it for you. So try to use those sparingly. It's like having like an ugly jacket in your closet. You know it's there somewhere, but you don't know where it's at, like because you haven't retrieved it in a while. So you have to sort of sift through your brain trying to figure out, okay, well, how do I calculate this limit? So that retrieval piece is huge. It's like a lot of people will say, like myself included, I had test anxiety, just hated taking tests. It's a real thing, but I think, the counterpart to that is just the ability to be able to recall a specific problem or a concept. So use that sparingly. If in theory you're keeping up with this, so you don't have like 20 hours worth of homework to do the night before the exam. But yeah, those are resources available. Any questions on this interface or layout? Okay. Sometimes this stuff is picky. Like if you enter an interval and you forget the comma in the middle, it's going to count it wrong. So I would always encourage students that, if you don't have the time or you don't want to go back and correct that, then just please email me and say, hey, can you look at question whatever from section 2-4, and then I'll look at it. If you forgot like a period or a comma or a bracket, or you rounded to 3 decimal places instead of 4, usually those are things I can give you points for. So just keep that in mind if you don't want to have to redo it for like a syntax error or something, or rounding. Let's see, is there anything else we should mention? No, I think that's it. For the homework, the quizzes are a little bit different because they're timed. And for each quiz you have 2 attempts. So it'll say right here, attempt 0 out of 2. So whatever your best score is out of those 2 attempts it takes, and that's your quiz score for that quiz. It'll say you have 120 minutes to complete. You want to make sure that you have a chunk of time. Again, it might not take you 120 minutes to complete, but you definitely want a chunk of time where you don't have to leave or do something like that when you start a quiz. The quiz actually covers usually a couple of questions from each section, so that'll probably be the last thing you do. Like if you're keeping up with the homework as we finish some sections in class, the quiz will be the last thing because it comprises the whole unit. So once you start, there's really no option to do anything. Like you can't save, you can't print. There's no like sources of help. Sorry, this is illegible. And it doesn't tell you if you get it wrong till the very end. So once you submit the quiz, it'll then show you which ones you missed. Again, if you miss round or miss a comma, bracket, whatever on a quiz, please let me know. I'm happy to fix that. Sometimes your fingers slip, you're not paying attention, it's totally fine. So yeah, usually the quizzes have 10 questions to them. So again, make sure you have a decent amount of time set aside before you do the quiz. One other thing I want to mention on the homework, you can email me. So like if you ask the instructor, that'll email directly. Just sort of be specific if you can, like what's the nature of your problem. instead of just saying, hey, I don't understand this, or something like that. Just try to be as specific as you can. This number here, this 2.57, this is section 2.5. This 7 is actually, if you look in the textbook, in the back of that section 2.5, this problem will be similar to question number 7 in your textbook. But as far as the homework set goes, we're on question number 1 of 24. So if you can remember that, it's not a big deal. It's just, it's easier for me to find. If you say, hey, on 2.5.47, it takes me a while to cycle through. It's actually question 13. It's similar to question 47 in your textbook. So that's the difference between those numbers. It just helps me out a little bit if you're emailing me questions. Not that big of a deal. Okay, yeah, I think that's it. All right, so those are the main things that we do online. Homeworks and quizzes there. There's a study plan. There's additional problems you could practice or quiz. These things aren't graded. But if you want additional supplement problems, then you can review them here. The gradebook, I don't use my Math Lab's gradebook, so please don't go buy the gradebook here. The gradebook that I use is the D2L's gradebook. So that's the gradebook that I'll enter your grades in. So in the homework, we had a textbook link. It'll pull up that specific section of the textbook. You can also go here to the multimedia library and select, if we're in section 2.2, you can select that. And sort of whatever you want to look at. If you just want the textbook, then you would select this option. Click on that link. It downloads this file. This is can y'all see that? It's a CDF file. Oh no, the board's not that great. So they're .cdf files. And so for the interactive figures on some of the homework to access the textbook, you do need that Wolfram CDF player to access those figures. But anyways, we have this file that's section 2.2 of the textbook. It's full color. Some of the figures you can move around and mess with. And that's another option to access the book itself. So let's see where we have our figures. Yeah, so anyways, it's another option. There's a static ebook option here. There's an interactive ebook option here. So there's really multiple ways to access. You can even go to chapter contents. It should have so they even have answers to the exercises from the textbook. So that's basically your student solution manual. That was under chapter content here. So mess around in here if you want. There's other resources that are super helpful, I think. On this course home here, I believe should be. They used to have a link. Okay, I guess they got rid of it. There used to be like a browser check that they had, where you could run the browser check, but I don't see that. So again, if you're gonna pay for this or access it temporarily, I would try to get on that just to make sure everything's working. Even if you don't plan on doing any homework this week, just make sure that you can access the assignments and everything's displayed correctly and all that kind of stuff. The sooner we can address these issues, the better. Do y'all have any other questions? One other thing that I have here on our homepage in D2L is this grade tool. So this might be more useful towards the end of the semester. Let's see. No, that doesn't look any better. Anyways, it'll look better once they fix this or on your computer. But it's basically there's sliders for your homework, your quizzes, or your homework average, your quiz average, and your exams. So you can mess around with this and see scenarios. You know, if this were the case, I'd have a 70 in the class. You know, but again, just to kind of illustrate, like if we had D's on all of our exams. So if we had D's on all of our exams, and this is of course a D for the overall course grade here, because our homework and our quiz averages are at 70s. But if we, you know, even if the homework average is a 94, you see that's now a C. If the quiz average is better, it's a higher C. I'm not condoning like failing all of your exams, but I'm just to kind of illustrate the power of what the homework and quizzes actually contribute to your grade. Super important, because especially the homework, you have so much control over the homework. If you've got a 95 on a homework and you don't like that, then just go back to the problems you missed, and then you have 100. Did you have a question?
Yeah, does the final exam, if we get a better grade on that than one of the previous exams, does
Right.
that replace it?
Correct. Yeah, the final replaces your lowest exam. So if we had a 62 on exam 1, a 64 on exam 3, a 64 exam 2, 65 exam 3, and let's say we made a 75 on the final, then you need to look for your lowest exam grade, which was a 62, and replace that with the final 75 as well. So again, there's a lot of variables still in play right now, but as we get towards the end of the semester, that can be super helpful, especially like once you know kind of where all your other grades are. Hey, what do I need to make on the final to make a C, to make a B, to make an A? You can totally see it right there. So, yeah. Any other questions? All right, so course materials, content, that's where everything will be. I'll post our class notes here. We have a module for blank notes, and I'll put the completed notes here. So everything we write down on the board in class will be put there. I do have guided notes, I guess. I've printed out the first 2 sections. But moving forward, if you want those guided notes to save you a lot of writing, so you don't have to write down theorems and definitions and all of that kind of stuff, then for the next class, look at your schedule, see what sections we're supposed to cover, and print that out beforehand. I do have the first ones provided, but now that you know, if you want those guided notes, then please make sure you print them before you come to class. Let's see, anything else? There's a module here for my math lab information. So like a flow chart, if you have certain issues, you could remedy that through the flow chart. So that's, I think, usually important, the first couple of weeks, because there's always people that have issues getting it to load properly. So that's also another resource that you have there. These slides are from our textbook, so they'll be like the definitions and the theorems if you want to look through those. Most of the important stuff from our textbook from those slides are already in the guided notes, so you shouldn't have to print off the slides unless you want to. Okay. So yeah, if you want these notes, make sure you print them. I think if nothing else can save you from writing a ton of stuff. More attention. Does anyone have any? Yeah.
A few questions about the exams.
Yeah.
And one of them is if we'll have all the time for this class, the 2 hours and 15 minutes to
Correct.
take.
Right.
And then the other is if there will be partially in multiple choice, or if you haven't decided that yet.
Yeah, so the exams are taken in class, so you do have the full 2 hours and 15 minutes to complete the exam. And yeah, all exams I usually have like some true false, multiple choice or fill in the blank type problems that are more conceptual. So those are always fun. Yeah, any other questions?
In general, do you think students have a hard time fitting in, like, the exams within the 2 hours and 15 minutes? Like I know with my pre-calculus class, like, you had to really use your time wisely, like, you had to be really efficient. So, like, would you say the exams are around 2 hours and 15 minutes, like, in length?
Yeah, I mean, and it's kind of depends on the student, right? Like I've had students finish exams in an hour. I've had students not finish. Most of the time it's because they come in late. I think if you've done the homework and you've studied, the exams should be pretty doable within 2 hours and 15 minutes with room to spare. It's kind of arbitrary because they'll say write an exam, take it yourself, however long it takes you to take it, multiply that by 4, multiply that by 5, multiply that by 6, and that's how long it takes students to take it. There isn't a universally agreed upon multiplier, so it's really hard to gauge, like, okay, this test took me 25 minutes to take. You know, I can only estimate it, but I know from previous courses, it's usually not an issue if you're prepared. Yeah.
For like the exam, do we have to get like the whole like question right in order to receive credit, or if like we've got like I don't know, like say some parts of the question right and we showed our work, is there going to be like partial credit awarded for that?
Yes.
Or, okay.
Yeah, so I do give partial credit. It's not all or nothing.
Can we use a calculator for the whole test, or are there going to be non-calculator sections?
Yeah, I don't have non-calculator sections, so the whole exam, you can use your calculator. Yeah. The main thing, like I said, on the exam is being neat and organized and showing work. That's usually where people will mess up. If you can show work, even if you're doing something wrong, those problems that sort of build off of each other, like it's, you know, hey, find this, find this, find this, and then graph it. Like if you mess up on an initial step, then I can just take off points for that initial step and then look at your wrong work. And if everything that you've done is based on your wrong work is correct, then I don't take off points because you made a mistake, and based off that mistake, you were still doing everything correctly, but you just had made that mistake, right? So the more work you can show, the better. I honestly think I'm pretty generous when it comes to grading exams. There's a lot of pressure. It's like 70% of your grade. You've got one chance to show somebody you know what you're doing, right? So I try to be as lenient on grading exams as I can. Yeah. Any other questions? Yeah.
How difficult would this class compared to like a pre-calc class?
I don't know. I think that's relative. Like the way I see it, like I see it pretty comparable. Others that have taken Calc 1, they might see it differently. But I think what it is calculus is you take algebra and you take pre-calc or trig, and you throw this idea of a limit into that with some other concepts, and you've got calculus. So if you're weak on algebra, like simplifying, factoring, trig, those things are definitely the skills that I see lacking in calculus, because I think calculus is like 80% algebra and pre-calc. Like the calculus stuff is like 20%. It's like, hey, here's a calculus concept. Now you got to do all this algebra to figure out what it is. So I don't know. Maybe someone that you know has taken this course could answer that a little bit better. But I think they're fairly comparable.
I was wondering if you're going to put a lot of focus on units in the class, because I know some math teachers do a lot of unit conversion.
Yeah. So that I don't know. Maybe for better or worse, depending on who you are, there's not a lot of time to do physical applications. We spend so much time with like the fundamentals saying this is how you do this is how you do that, and then we maybe have this much time to look at an application or two. So like in the few sections that we have that are actually application-based, units are naturally important. That being said, I don't think I usually take off for, if it's 135 meters per second and you just write 135, I probably wouldn't take off for that. I think that's pretty nitpicky. I just assume that everybody knows how to work with units, and if you mess up, you mess up. I don't really put a lot of emphasis on that contributing to your grade. Yeah. Any other questions? So this, I don't know, this is a somewhat difficult class, but I think at some point, hopefully all of this stuff you've done in algebra and in pre-calculus, a lot of it sort of fits into what we're doing in a new framework that I personally think it's easier to understand. Like when you talked about let's see, vertical asymptotes, and it said, oh hey, there's a vertical asymptote when this happens, but there really wasn't any reason why. Like a lot of that stuff we learn the why in this class, and I think it's easier to remember than how you remembered in pre-calculus or in algebra. So hopefully this class does to some extent tie in some concepts that you've already done, and makes a little bit more sense out of it as to why it does what it does. So yeah, that being said, if there aren't any other questions, I'm going to call roll, and then we'll take a break, come back, and we'll start 2-1. Okay. If you go by something different than what I have here, please let me know. Abdul Rahman. Kevin. Lucas.
I'll go with Luke.
Luke, all right. Ryan Beck. Moshi. Ryan Brim. Paul.
Here.
Where you at, Paul? Grayson. Milo. Rihanna? Raina? Okay, sorry about that. Gunnar?
Here.
Max? Joseph? Omar? Nick? Juan? Trevin? Richard? Devin? Daniel Nall? Daniel, is it?
No.
Whoa?
No, that works.
Okay.
No, like,
Well, so what's your last name?
no.
Okay.
Like, yes, no,
Okay.
yeah.
All right. Where's the other Daniel? How do you say your last name?
No.
No? How do you spell it?
N-A-L-L.
N-A-L. Spell your last name?
NGO.
N-G-O. Okay, how do you pronounce that?
No.
No. All right. Sorry for the confusion. Thank you all. Adam? Lindsay?
Here.
Eduardo?
Here.
Carmela? Antonio? Minnie?
Here.
Maya? Kai?
Here.
Esme?
Esme.
Esme? And Amber. Okay. Anybody's name I didn't call? All right. I'll probably call a roll for first few 3-4 weeks, just to try to get everybody's name down. I haven't decided yet, but usually people will tend to sit where they sit on the first day, but I don't like asking people to sit in the same place every semester, but I might do a seating chart. And if I do, I'll let you know, but that would mean you sitting in the same spot all semester. Will help me with your names. So if 100-something students, I try to remember names, but it's so hard. So don't take it personally if I see you in the hall and you're like, "Hey, Cody," I'm like, "Hey." I try as quickly as I can, but it doesn't always work out. All right, so we'll take a 10-minute break and then start 2.1.
We should bring our
You still have your.
The second pillar is integration. And integration tells us stuff like area, volume, work, force, surface area, etc. Integration actually does more than differentiation does. Differentiation is just basically an instantaneous rate of change. There's a lot of different interpretations for integration. We see integration in sort of in 4.9 and in Chapter 5. So we end with sort of the tip of the iceberg for integration, and then if you go on to Calc 2, the rest of Calc 2, or a good chunk of Calc 2 is devoted to more integration stuff. But nonetheless, you can't have any of that without this idea of a limit. So what we're doing in 2.1, it's just the basic idea of a limit. It's more implicit in 2.1 as far as what a limit actually is. And we're going to look at some numerical computations of a concept that should be familiar to us. And we're going to use that computation with a familiar concept to sort of illustrate the idea of a limit. And as we go through Chapter 2, we'll talk about its properties, how to compute them, how you actually define what a limit is, and all of that kind of stuff. Okay. So do y'all have any questions before we get into it? All right. I might have to reopen this. Sorry, there's sometimes a discrepancy between files that I create versus what you actually have, so I apologize for that. Oops, wrong one. I swear it was all there. It's all there for y'all, right? So weird. Just be sort of, yeah, all right. Well, that's not a great start for technology. All right, so well, I guess I'll just write some of this stuff down, but you have quite a bit of information there, I believe, as far as recalling a concept that you've looked at in the past, which was the average rate of change. And so the average rate of change was nothing more than the slope that connects 2 points on a particular function. So I'm going to need to write this out, otherwise the notes won't be complete. The average rate of change. And That phrase rate of change is sort of a generic placeholder for something that you're measuring. It's the average speed, average temperature, average something. Is the slope. If I have to refer to this, I'll abbreviate it. Average rate of change. Is the slope between 2 points. Point 1, we'll just call it A, f of A. And second point, B, f of B. So what we're actually going to do is we're going to look at an average rate of change and make a bunch of computations with the average rate of change to illustrate the idea of a limit. And maybe already intuitively you have a notion of what a limit is in your head. If you've taken this class before, even if you haven't taken this class, you probably have some sort of idea of what a limit is. So does anybody think of anything in particular when the word limit's thrown out?
Like moving closer and closer to like a certain point.
Right. Yeah, like getting closer and closer to something, right? It's kind of paradoxical in the real world to say I can get closer and closer to something, but never actually touch that number or touch that quantity or thing. But in the sense of real numbers, it's not a paradox. Like I can get as close to 0 as I possibly want without ever being at 0. So that's a limit, and it's sort of this infinitesimally small thing, and another limit would be what?
Could be the boundary, or kind of like domain.
It could be, yeah, in a mathematical sense, yeah, a limit, it does have certain restrictions on it, yeah. But like an infinite thing, right? Like I can approach infinity. So infinity is not a thing, but we can compute limits at infinity by just saying, hey, this thing's just getting larger and larger in a particular direction. So you kind of have two limits in that sense. One, you're getting closer and closer to something that's finite, and the other limit is you're just getting larger and larger or further and further out. That's kind of the idea of a limit, but illustrating this, I think we have illustration there. You know, we have some function here, f of x, at a and b, let's say. And that gives us 2 points. Oops. And if we look at the slope of that line, compute the slope of this particular line, that is the average rate of change. So this is the average rate of change. And so your example below, it's pretty straightforward, but I travel, sorry this didn't show up on the board. I've got to complete this, so if you miss class, these are all available. You don't have to ask somebody for them, but I need to make sure they're complete for those that aren't here. So I travel 20 miles to school in 40 minutes. What is my average velocity? AG. Sorry, this pen is super sticky. What is my average velocity here? So if we're going to look at it, like we don't need to know anything about the particular trip. I don't need to know a position at every given time. If all I'm asked to compute is the average velocity. And again, that velocity here is the rate of change. So, you know, for simplicity's sake, we would say, all right, well, that's my house. Oh, that's true. That's straight. Typically, time is the independent variable. So we have our minutes here, we have our miles here, and it takes me 40 minutes to travel 20 miles. So I've got the point at which I started and the point at which I end. And again, my position throughout this entire trip, we don't really care about, right? It could be something like this. If all we're after is my average velocity from when I leave my house to when I end up at school, all we're going to do is compute the slope of that line that connects those 2 points. So regardless of what the function's doing, we're just computing that slope. So our y values and our x values. Let's say that's the slope or the average velocity. Sorry, can you hear that? It's almost like nails on a chalkboard. That's what we're computing there. Okay. So I know our units were miles and minutes. We just compute, 1/2 mile per minute, 2 miles per hour. And see that on average I travel 30 miles per hour, even though we know, that's not the case at any given time, right? At any given time, how fast am I going? Just look down at your speedometer, that's how fast you're going, right? So even if I'm going like 65 miles per hour at some point, 75 at some point during this trip, on average I travel 30 miles per hour. So this computation is what we're going to use to sort of illustrate the idea of a limit. And then as we move forward, like I said, in chapter 2, we'll start to look at particulars. Do y'all have any questions at this point? Okay. So some terminology. I believe you should have this written down below. The terminology here has nothing to do with the trig functions. It's a completely different concept, though they share the same name. So we have a secant line. That board is super scratched. We have a secant line, which is a line that cuts through a curve. We'll just say a function. Okay. So nothing to do with the trig function. It's just the Latin word as whatever, however you pronounce that in Latin. I'm not going to try. That it just means to cut. So the lines that we've all computed slopes for up to this point have all been secant lines. When we actually get to the concept of a tangent line, we'll sort of make that precise and clear. But a secant line, computing the slope of a secant line is the same thing as computing the average rate of change. It's the same thing as the slope. So it's just the standard slope we all know and love. Okay. So we'll go ahead and say that here, the slope of the secant line is the average rate of change. I guess abbreviated, we could say that the slope, M for slope, and then just have a subscript here for secant line. The slope of the secant line is the average rate of change, which we defined up there, f of b minus f of a, change in y over the change in x, b minus a. And then we have a tangent line. And so tangent, again, not related to the trig function. The tangent line itself comes from the Latin, whatever that is, and it means to touch. So a tangent line is a line that just touches a function in one spot, or one point. So if you could imagine, you know, in algebra class or whatever, they say, hey, here's 2 points. What's the slope of the line through those 2 points? What we can do eventually with calculus is to say, here's 1 point, what's the slope of the line at that 1 point, at that particular point? So that's kind of what a tangent line is. It enables us to compute the slope of the line at a single point, not through 2 points. All right, so we'll address that as we progress. Most of this stuff about tangent lines, though, doesn't come in until chapter 3. But we will see it here in this section as well. Do y'all have any questions? Yeah.
It's kind of going on a tangent, but do you have then, or is this going to be a lot of trig functions as well? I didn't ever ask that.
There's not a terrible amount of trig stuff. There is a decent amount, but definitely not what you saw in pre-calc, where you're like proving identities and, you know, like the basic stuff of trig at this point you should know are some basic identities and some values of sine and cosine. With values of sine and cosine, you get all of the other trig functions. So if you know, right, you know the reciprocal relationships between the trig functions, Pythagorean identities, and values of those things. Most of that other stuff we can kind of, you know, use other algebraic knowledge to get to. Yeah, so that's all good. Okay, so we're going to look at an example where we're given a position function. Position function S of t. So S is our position at some time t, as negative 16t squared plus 96t. So in how we're going to illustrate the idea of a limit is, let me just kind of give you an example here. So we've got some function. How we're going to illustrate the idea of a limit is we're going to say, all right, well, algebraically, we can compute all-day slopes on a function between 2 points. So really what we want to look at is sort of numerically, computationally, is how would I go from computing this slope, which is my average rate of change, to computing the slope of this line here at that single point. So that's kind of what we're going to do through some numerical computation. So if you have a calculator, now's a good time to get it out. I guess I can refer to the notes that I gave you all, but we do have 3 computations we want to perform with this function. All right, so the position function, S is in feet. Time t is in seconds. Okay, what we want to do is 3 computations where we find the average velocity between the given times. And just looking at example 1 or problem 1, problem 2, problem 3, what's happening? Like, what are we doing there? We are computing the average rate of change or the average velocity over those time intervals, but what's happening to those time intervals? They're getting closer and closer to 1.
One, but getting slightly off of one.
Right, right. So, I mean, basically we would stop there and say that's the idea of a limit, where we're getting closer and closer to something. Like that's pretty much the idea of a limit. So I'll pull up a figure in a second, but let's go ahead and compute this first one together. From time equals 1 to time equals to 2. Yeah, sorry for that noise. There's literally like deep scratches in this board. I can't do anything about it. So from time equals 1 to time equals to 2, we're computing the average rate of change or the slope of the secant line. Remember, they're one and the same. Slope of the secant line versus the average rate of change versus rise over run, it's all the same. So we've got 2 x values, if you will. So what we need to compute is we've got our function s of t up there, and so our y values and our x values. So we need to compute s of 2 minus s of 1 all over 2 minus 1. So there's our change in y over the change in x, or the change in position over the change in time. Keep in mind the units here, just so we can kind of get a sense of, we are actually computing a velocity. The units for our position are in feet, and the units for time are in seconds. So whatever number we come up with here, 5 feet per second, that is a rate of change, that's a velocity or a speed if you think about it that way. So we need to compute our function at 2 and our function evaluated at 1. So let's just take a second and compute those values, just so we can make sure we're all... It's probably been a while since you used your calculator, but hopefully that computation's not anything foreign to you. So did anyone get S of 2 yet? 128? Is there any, are there any decimals, or is it exact? Okay, so S of 2 is 128. We're going to subtract off S of 1. What's S of 1? 80. Okay, so again, feet per second are the units, and we end up with 48 feet per second. So given that particular position function, which all it does is track location at every given moment in time, given that function from the first to the second second, on average we were traveling 48 feet per second. Any questions? All right, so why don't you take a moment to compute the next two, from time equals 1 to 1.001, and from time equals 1 to 1.0001. remember with the slope, it doesn't matter the order. It's just the things in parentheses for the y values or the x values into the function just need to line up on the bottom. So we could also compute s of 1 minus s of 0.001, or sorry, 1.001, as long as the bottom was 1 minus 1.00. It's all the same. So what did y'all get here for number 2? 63.984. And again, the units are feet per second. Did everyone get that? Did y'all have enough time to do example 3? Yeah? Okay, so let me just write this here. Example 3, the average velocity. We're just abbreviating that. Average velocity in 3 was, what did you get?
63.998.
63.994. Anybody else get that? Feet per second. All right, our computation here. Same. Yeah. So that's just s of 1.0001 minus s of 1 all over that change. All right. So I mean that's all well and good. It's really what actually is unfolding here that we're going to attribute to the idea of a limit. Okay. So I think it's easier just to show you as opposed to drawing it what's taking place. Does anyone have any questions about what we've done? So these are just slopes between 2 points. Sometimes they just give you the interval like this here, with a closed interval from 1 to 1.001. It's the same thing, same kind of notation. All right, so here in the black is the function itself. And what we did was we said, all right, well, from time 1 to time, what was our first one? 2. So the example 1, we computed, our computation was the slope between this point from time equals 1, position of 80, to time equals 2, position of 128, right? So the numerator was 128 minus 80, divided by 2 minus 1. Right? So that 64 gave us the slope of this green line here. That's our secant line, that's our average rate of change. In example 2, the second point was now at a time of 1.001. So I can't get that close. But what we're doing is we're saying, all right, well, what's the slope between these 2 points? That's the average in green. And then we say, well, let's make that x-coordinate 1.96. Let's make that even closer to 1, and then compute that slope. Make it even closer to 1 and compute that slope again. And then so if we keep doing that for successively smaller and smaller time intervals, then notice what we're virtually describing is the slope at that single point. Does that make sense? So that's visually what we're doing. We're just computing the slopes of all of these green lines. All the while, we're just making that x value or that t value closer to something else that's fixed. Here, fixed at 1. And you see what happens. The slope of the secant line, the average rate of change, does approach a unique number. And that unique number is 64. Touching at 1 point, that becomes the slope of the tangent line. So this is basically like we're seeing a secant line over smaller and smaller intervals turn into a tangent line. And that process of looking at smaller and smaller intervals is that of a limit. So that's what a limit is. It says, hey, what's the slope of this line as t gets closer to 1? That's all we do when we talk, that's all it is to talk about a limit in sort of this mathematical sense. So do y'all have any questions on that? So I'll just put this static image in your notes, just so maybe you can remember. This is, excuse me, interactive figure in your textbook, so you have access to these kinds of things. And then we'll also look at some other numerics, but we've only computed 3 different scenarios here. The first one, you know, we were, I guess, a significant distance from 1, right, from 1 to 2, and then we made a really big jump. Now compute from 1 to 1.001. So from 1 to 2, it was 48 feet per second. When we were pretty close to 1, we saw that it's 63.984, and then even closer, it's 63.9984. So you start to see that difference in the average rates of change here as we get closer to 1, sort of jump less. So it jumps a lot here and then not very much here. So based on these 3 computations, what we can do is say, all right, well, I've got a few values for the slope of a secant line over smaller and smaller intervals. And based off of those numerics, if I were to continue to get closer and closer to 1, that's the idea of a limit. If I were to get closer and closer to 1, what would I suspect that number to approach? What does it look like our computation is actually getting closer to? 64. Yeah, we saw it here, 64. So if I were to do from 1 to 1.0000001, then it's going to be 63.999999, right? So can everybody see that from the limited kind of information that we've looked at? Okay, so that's the idea of a limit. So not only do we get an idea of a limit here, but it also illustrates how we connect these 2 concepts between sort of an average rate of change, on average how fast did I travel, versus at a particular moment in time how fast am I going, looking at my speedometer. So what we see is the average approaching an instantaneous rate of change. Do y'all have any questions on that? Let me see if there's, if we look at a, sort of just a few more computations. We're not actually going to do them, but so here's a couple more that I'll put in our notes that we did in compute. So that's the idea. If we compute, remember these average velocities are nothing more than the slopes between these two points. And again, the 2 points aren't explicitly given to you, they're implicit. You've got to plug these 2 values into the function, but we can sort of see the evolution, I guess, at these slopes successively as this value here, rather the other one, gets closer and closer to 1. So we're taking this value, we're fixing the left endpoint, if you will, and we're just making this value closer and closer to 1. So that's the idea of a limit. Yeah.
So are these like average velocities just like specific to this problem, or are they general?
Yeah, these are specific to that position function.
Okay.
If we had a different position function, the process would be exactly the same. However, these values would be different because we have a different function. But yeah, still, this is still specific to that problem. Sure. Any other questions? So I hope that, you know, in practice, that the idea of a limit is actually pretty straightforward. Like I said, we end up looking at 2 of them, 2 different types of limits. but in nature they're really infinite, right? Like infinitely large and infinitely small. So we have, I don't know if you have this page. We have observed the nature of the limit. There's a few ways to write this, but we can say that the instantaneous velocity how do I say this? Instantaneous velocity. I guess more generally, it's an instantaneous rate of change. We'll talk about the notation in the next section, but what we did was we said compute the slopes. We'll just keep this notation, S of B minus S of A. So the change in position divided by the change in time. B minus A. But to get the specific instantaneous rate of change, it wasn't sufficient enough to look at just the slopes, because if we just looked at those slopes, then all we would get was 48, 63.98, and 63.998. We had to, in order to get that instantaneous velocity or instantaneous speed, what we had to do was let that time value approach 1. So that, we'll see this notation in the next section, don't worry too much about it, but we had to compute the limit as t approaches 1. So basically that condensed notation is what we did in those 3 examples. We could have kept going, but that's basically this. In other words, the instantaneous rate of change is just the limit as t approaches something on the slope of the secant line, or the average rate of change. We'll just say as t approaches A, I don't know. So as t approaches something on the average rate of change, we get the instantaneous rate of change. So there's quite a bit of examples in your homework where you're having to compute things that we just computed, and there will be one question like that on the exam too. So it's tedious, it's time consuming, but it does take something we're already familiar with, and through these numerical computations illustrates the idea of a limit. That's kind of the main idea. Do y'all have any questions? So there is one generic problem like this in your homework. I guess generic, maybe in the sense of, so sort of like the same as what we just did, it's just phrased a little bit differently. So I'll just say like in 2.1's homework, what you have is, they say something to the effect of find the average velocity. So when you see that word average, average is always just the slope itself. The instantaneous part comes from looking at the averages over smaller and smaller intervals. That's where the instantaneous emerges. This is like find the average velocity over the time interval. It might not even say that, but 1 to 1 plus h. So the point of that example is you're still doing the same thing. It's just to get you to think a little bit more generally about what we're doing. So all of those ones that we looked at, I'll erase this, but it was from 1 to 2. and then from 1 to 1.1, and then from 1 to 1.001, so forth. So all they've done here is said, well, this thing's staying the same at 1 each time. 2, 1.1, 1.001, et cetera, et cetera. All of those other values could be described as merely a step away from 1. So that's all this h is. So if I tell you that h is 1, now I'm looking at this interval from 1 to 2. If h is 0.1, I'm on the interval from 1 to 1 plus 0.1, which is 1.1. Does everybody see that? It's more generic, and I think it's worth talking about. So on this interval here, h is equal to 1, h is equal to 0.1, and so forth. H is 0.001. So, if you made a couple, 5, 10 computations from 1 to 2, 1 to 1.1, et cetera, et cetera, et cetera, it's super tedious to keep doing that over and over and over for the same function. So computing on the interval from 1 to 1 plus h gives you not a specific number, like when we compute the slopes on this interval, we would get 48, specific number 63.9, right? When we compute the slope over this interval, we actually get a slope formula that's simply in terms of h, right? Because we're not plugging in a specific number for this value here. When we plug in specific numbers, we get a specific number in return, and that's our slope. But we don't have two specific numbers to do that with. So when we compute the average velocity on this interval, it's more generic in terms of h. What we're going to get is a formula involving h. So we get some function of h. Let's just say that I've computed that and that I got it to come out to be, I don't know, 2h plus 3. It's probably not the case for the one you're going to end up doing, but let's just say that I compute this. I'll make it more specific, yeah.
Is h a parameter or a variable?
Yeah, so h is, you can think of it as either here. But all h is it's like, here's this function. Here's this function, here's 1. And instead of looking at what's the slope that connects these 2 points, and then the slope that connects those 2 points, like all we're gonna do is make these other points over here more general. And we're just going to say that's 1 plus h. H is merely a step size, or the distance you are from this point right here, this value here.
Just so you can compute it faster.
Yeah, so you can compute it faster. Does that make sense? So it's more of a shorthand way to compute multiple computations. Like if we had 10 intervals to compute, even if it didn't ask us to do this, it's more efficient to do this. If it's confusing, then don't put a lot of stock into it. But I think it's, as far as like where we're going with all of this, as far as derivatives go, it's better to think of it in terms of a step size as opposed to 2 fixed things each time. So the average velocity that we compute here, again, depends on the function, but it's going to be our position function at 1 plus h minus the position function at 1 all over 1 plus h minus 1. So whatever this, we haven't specified the function, of course, that's going to be given to you. You have to evaluate it at 1 plus h, and naturally when you evaluate a function at 1 plus h, you're not going to get a number in return. You're going to get something that involves h and some other numbers. Then we subtract off s of 1, then that's going to be a particular number. We've got 1 plus h minus 1 on the bottom. So that just gives us h on the bottom. You've got a function of h here. This is a number. And then you combine those, it's all over h. You factor out whatever, simplify that as much as you possibly can. And let's just say you ended up with, let's just say that it was that this was equal to 2h plus 3, after we simplified and combined like terms and all of that. So that says, what this says is this function of h right here is the slope between 2 points on that curve from 1 to any other value. All I have to specify is how far I am away from 1, which is h, and then plug that in, and we would get the actual slope. Is that clear?
Would you be able to end up plugging like 0 into that and get your tangent?
Right, yeah, so notice when we think of it this way,
Or will you end up with the 0 in the denominator and not have it?
So yeah, that's the thing with limits, what we have to talk about, because, you know, like if we're looking at it as sort of this step size, instead of like specific intervals, if we say, you know, let's keep with this picture that we had here. Here's 1, and here's 1 plus h. There's our average velocity, is that slope. So in order to do what we did in that last example, what has to happen to h for us to be able to compute the slope of a tangent line, or the instantaneous rate at that single point? Everybody see that? Yeah. What has to happen in that situation to make the right point, if you will, closer and closer to the left point? Right, it has to get smaller and smaller, and specifically what has to get smaller? Well, the decimal place in the numeric sense, right? We took this point, it was 2, and then it was 0.001, right? So it was totally clear in those concrete examples that, hey, that right endpoint is just getting closer and closer to 1. In order to make this thing, the 1 plus h, get closer and closer to 1, what has to happen to h?
It has to be smaller each time.
Right, it has to get smaller and smaller. In other words, it has to approach 0. Because remember, h is just the distance we are from 1. In order to be here, in order to be there, that step size or that distance has to be smaller and smaller. It has to be virtually 0.
But it can't be 0, or else it will have a 0 as a denominator, or...
Right, yeah, exactly. So that was, sorry, what was your name? Adam. Adam's comment was back here now. Well, if we let h approach 0, then isn't there an issue? Because we've got an h in the bottom. You can't divide by 0. So that's what we'll see in the next section. The limits don't care about what's happening exactly at time equals to 1 or as h approaches 0, right? So there's a big distinction between a function value and a limit, and we do see that in 2.2. But in short, if h approaches 0, we don't have any issues. We can compute this. So think about it, you know, as far as like numerically, if someone said, hey, compute 3 divided by 0, what would you tell them that value is? It's undefined, right? You cannot divide by 0. You can't have nothing downstairs, right? It's fine to have nothing upstairs. That just means I have a one-story house, right? Because I don't have an upstairs. But if I don't have anything downstairs, then I'm in trouble. So think of it this way. This does not exist. You can't define what it means to divide by 0. Does everybody remember that? Yeah.
Can't it still technically be a number, even though it doesn't exist, can't it be, I guess, an asymptote or something similar?
Could be, right. You got to remember, in the sense of a limit, though, you're never going to be asked to compute 3 divided by 0. Even if the denominator is approaching 0, what does that mean? It doesn't mean it's 0. It just means it's getting closer and closer to 0. So if I take 3 and divide it by a smaller and smaller number each time, what happens to that quotient?
It grows closer and closer to infinity.
Right, it gets larger and larger, right? So we can't actually compute that value in the sense of a limit. And these are all things that we end up addressing, because it's not as straightforward as it appears when we're doing these types of things. You start to see a little bit of like, you're already thinking about issues. Well, hey, if this thing's going to 0, doesn't that mean that's undefined? And it's not. It's intuitively, yeah, it would seem that way, but it's not the case. So there's a lot of, the rest of chapter 2 is kind of devoted to addressing those things.
Would it ever go negative, go to the other side?
Could, yeah. Yeah, so we just used this h to illustrate points that are to the right of 1. We could say h is -1 and be on the other side or to the left of 1.
So you could do like 6 plus h, and then minus s of like 6 or something like that.
Yeah.
And then move on.
Yeah, yeah. So this particular example on your homework, you end up computing this kind of generic thing, and you get, hey, my average velocity is some function involving h, and then you can come back to these specific examples, and you can say, hey, the slope or the average velocity on the interval from 1 to 2, when h is 1, just plug that 1 into the 2h plus 3. On 1 to 1.1, h was 0.1, so you just plug that 0.1 into the 2h plus 3. Okay, so I'll just put that here. This gets plugged in to the 2h plus 3 to give us our average velocity on that interval. This h value gets plugged again into 2h plus 3 to give us our average velocity, plugged into 2h plus 3 and the average velocity. So it's a little bit, on the front end, it's a little bit more involved, but on the back end for computing all of these, you can see it's a lot simpler. I really don't have a preference. The one we just did kind of together is more reflective of what's on the exam. But I do think this is a really good way to think about it. Someone have a question over here? Are there any questions on this?
Actually, so I guess the one question I have is, on the one we did, we calculated out like 128 and 80 for the numbers.
Yeah.
Do you want us to show the work for that each time? Or is it okay if we just plug it into a calculator and move on?
Yeah, so this 128 and this 80 are sort of intermediate computations.
Okay.
Like on the exam, a computation like this for one of them, just so I know what you're doing, would be acceptable. The other ones we could just kind of write out like this here. If you just wrote that out and then the answer, I'm fine with that. Any other questions? Okay, that's the idea of a limit then. And really we don't get to the formal definition of a limit, like how a limit is defined mathematically, until the very last of chapter 2. So it's kind of weird in that the last thing we talk about is actually how you define a limit. The next few sections are devoted to how limits work, kind of their properties and stuff like that. So if there aren't any other questions here, then we'll end 2-1. Go on to 2-2. So our kind of our working definition, our preliminary definition, as the textbook calls it, of a limit, this is sort of what's going to follow us until 2.7, until we get the actual definition of a limit. Hopefully yours is more legible than yours. But we've got some function f defined for all x values near a, and a is just some x value. So they're all, x values are defined near a except possibly at a. So that's a super important statement that accompanies our definition of a limit. Except possibly at a. What that means is the function itself doesn't necessarily need to be defined at that x value. Okay? So f of x, the y value, is arbitrarily close to capital L. L itself, capital L, is just another y value. And notice it's not precise, it just says arbitrarily close. How close is that? Just depends. Is it this close? Is it this close? It's a very nebulous definition right now. So if the function is arbitrarily close to this particular y value, capital L, for all x values sufficiently close but not equal to a, then what we write is the limit, if you can see that notation, that's red, the limit as x approaches a, or as x gets closer and closer to a, on f of x. You know, there's a few other ways to kind of write that out in language, but I want you to think of it that way. They're all virtually the same. So what it says is, we look at this function f of x, and we look at, as x gets closer and closer to this value, wherever that x value is, as x does this, what does y do? So that's basically how we answer the question for this notation. We should also say here that this L is a finite number. Sorry, I missed the... L is a finite number. In order to say you have a limit, that hopefully that's intuitive. If I say that there is a limit to this thing, it has to be a finite number. Whether it's a billion or a trillion, doesn't matter. If there is no limit, then we would expect that thing to just keep going, right? So if something does approach a limit, if the limit does exist, it has to be a finite number. Otherwise, there is no limit. Okay, so this L, the value of the limit determined by the function, as x gets closer to a, sometimes it exists, sometimes it doesn't. But it depends on the values of the function when x is near that a. It doesn't depend on the values at a. Okay, so the values near a, and again, a is just some x value that we specify. The limit, when we compute a limit, it never depends on the value at a. In other words, evaluating the function at a and computing the limit at a on that function generally are different things. Sometimes we'll see that they're the same, sometimes they're different. It really just depends on what's happening on the function itself. So there's a lot, there's a lot to digest here. The limits don't care about what x is. It does approach a. It doesn't care what's happening right at a. So the function doesn't even have to be defined at a in order for us to compute a limit. I just want you to think that when you compute a limit, it says, as I get closer and closer to this x value, on my function, what do the y values get closer and closer to, right? That's what this equal sign here is sort of misleading to say that it's identical to the L. It's not saying that it's identical to L. In the sense of a limit, it's just what is it getting closer and closer to.
So just to clarify, so like it approaches it, but it's never actually like the the value that you're approaching.
Right,
Okay.
right, how close can you get to 1? As close as you want, right? If you say, hey, I'm at 1.00000001, then I would just say, well, to get closer, just put another 0 in there and keep doing that forever and ever.
So in a sense, like if we were looking at a graph, like we have the 2 dots, we could in a sense think about those dots as like circles.
Yeah, so that's
included.
the open and the closed circles, right? The dots, the points included, the open circles or the holes not included. Yeah, and we can still compute limits around those things. So for example, we're going to use this figure and evaluate a few things. So find, the first thing we're going to evaluate is f of 1. So what is the function evaluated at 1? It's 2, right? Here's 1, here's the function evaluated at 1, it's 2. Okay. Then we'll look at the limit as x approaches 1 on whatever this function is. It's just f of x. So now we're thinking, since it's the limit, when you're evaluating limits graphically, you've got to think of the graph, the function itself, as the road, and it's the only road you can travel along. So in the sense of a limit, here's x equals 1, as I get closer and closer to an x value of 1, from either direction, what are the y values getting closer and closer to? They're getting closer and closer to 2, right? So on this graph, the x values are getting closer and closer to 1. What is this y value that we have got closer and closer to? Does that make sense? Okay, so the limit as x approaches 1 is also 2. Then we're going to evaluate f of 2. What's our function evaluated at 2? 5. Yeah, 5. Everybody see that point there? F of 2 is equal to 5. And then we're going to evaluate the limit as x approaches 2 on that function.
4.
4.
3.
3?
3.
What do y'all think? Is it 3? So we're talking about a limit now. We have to stay on the function to travel. When we say approach, just think about, driving towards something. So as x gets closer and closer to 2, here's our x values along our road getting closer and closer to 2. What are the y values getting closer to? Closer to this thing right here, right? The function's not defined there. We can clearly see that at that particular location it's not defined. But again, the limit doesn't care about that. It just says as x gets closer and closer to 2, what does the function get closer and closer to? And the function just gets closer and closer to 3. So I think we'll end it there. Do y'all have any questions on that? So I would recommend getting MML up and running and start 2.1's homework if you have time. I'll see y'all Thursday.
Another win.